So this is shifting a little bit. This isn't strictly a balloon payload, but a detector that's designed for a few different payload options. And so I kind of wanted to go through the characteristics of the detector and where we stand and what our plans are, which you have heard about in other talks today. AstroPix are originally designed for gamma ray space telescope that is very similar to the Fermi Large Area Telescope, so really like a large area plane of detectors. The main motivation for this is because unlike in X-rays, you don't have focusing optics that can focus gamma rays, and so your light bucket is just a huge plane of detectors. And so this is originally designed for TDAM. However, what we've seen with the performance of these detectors is that they really are good all the way into like the hard X-ray regime, and also can give us some really interesting things in the Moon to Mars space weather initiatives and other national security applications. And then I'm here on behalf of a very large team of people, so not just at Goddard, but we have collaborators throughout the country and throughout the world, and so just shout out to them as well. So go to the next slide. Or do I go to the next slide? Okay, cool. Cool, I have the power. So AstroPix is a monolithic active pixel sensor, and so this uses a CMOS technology where all of the signal amplification, digitization, triggering is all implemented within the chip itself. And so what that buys you, especially compared to previous technologies, is you get much better noise performance, you get higher efficiency, and you get much lower power than you would. And so for when you need really large really large detector planes, that's really where the benefit comes in. And so we've started developing these detectors based on a technology that was originally used for ground-based particle physics experiments, because gamma rays are basically particles in space. And we've been evolving these detectors, like I said, since maybe 2018, 2019, when we started characterizing them. The people who have done all of our ASIC development, so the detector development, are at the Karlsruhe Institute of Technology. So it's a research institution who have been developing these chips for about 2 decades. And so we've been utilizing a lot of that heritage and really designing something that we wanted for gamma rays. And that's really where the novelty of these detectors comes in, because on the ground they were designed as being particle detectors, and so they're really designed to measure charged particle tracks. What we wanted to do is basically combine a tracking and a calorimeter type of detector within a single detector, and so that's what AstroPix is compared to the previous iterations. And I'll go in a little bit more detail as to what that means. So our strategy has been to step through this in iterative fashion. So going from the original design, making modifications, and the idea was to keep a functioning chip as long as possible, with each step being another iteration that's getting us closer to a flight prototype. Our first flight prototype is the third version, so AstroPix V3, and that was delivered in 2023, and we've been integrating that into a sounding rocket payload, which was A-STEP, which you heard from Dan Violet earlier today. AstroPix V4 was another test chip, which advanced upon that, which I'll talk a little bit about later, and then V5 is going to go into a balloon payload, which you'll hear about later in the session, so I won't spoil any of that. So as I mentioned, this technology improves upon standard silicon pixel detectors, or say other silicon tracking detectors, say like TimePix, which is flown on the space station, because it embeds the charge collection, amplification, and thresholding all within the pixel. And then here on your left-right is a cartoon of what a pixel would look like. So the CMOS circuitry is about the top 5 or so microns of the silicon substrate, and all of the electronics are embedded within that well. The pixel itself is 500 by 500 microns wide, which seems really large for some applications, but it's actually kind of perfect for gamma ray applications, because a lot of energy is deposited, and so if you have smaller pixels, you just get the electron clouds being split among lots and lots of pixels, so you don't really gain anything. The challenge that we had in these iterations is reducing the power consumption, because when you're starting with a ground-based experiment, you can basically run right next to a power plant. You don't have to worry about powering the thing. Because, like I said, we were combining a calorimeter and a tracking detector within the same detector, achieving the full energy range that we wanted was also one of the challenges. And this is tied to achieving the energy range and energy resolution. We wanted to fully deplete a relatively thick detector because our pixels are also 500 microns thick. And so those things have been the real challenges, and I'll go into a little bit about how we've addressed them all. So I already mentioned that we've gone through 4 iterations on the bench. The 5th one is in production. And so we've done various testing. So the 2nd iteration we did radiation testing on. We've been stepping the power down, and we're almost at our power requirements. The big jump between AstroPix V3 and V4 was for V3, we had been daisy chaining the columns together. So we had kind of like stripsels instead of pixels. But we found a better power saving way to implement an actual true pixel in V4. So that's really exciting. So this is a true pixel detector. And then, like I said, we're excited to see what comes out of V5. So the first test that we did was we wanted to make sure that that these detectors were good for a radiation environment. So they were originally, like I said, developed for ground-based particle detectors. So we knew that really, really high particle fluxes weren't going to phase these detectors at all, because this is what they were designed for. But there was a question, especially about heavier elements, how would they impact the circuitry? And so we took the detectors to the LBNL Berkeley Accelerator Space Effects facility, and we ran various different ions and bombarded them against the detector. The 2 main types of single event effects we wanted to test were for single event latch-ups and single event upsets. And what we found was that there were no catastrophic destructions to the detector itself. Sometimes there were soft errors, so we needed to reset the chips, but this was very promising to show that this would be a good detector to use in space. So that was very promising results. The next test that we performed was just to measure the energy range, and we did this with a series of radioactive sources. So the way that these detectors work is that we use a time over threshold measurement to approximate to be a proxy for the energy source. So what happens is you have your threshold set to a certain voltage. As soon as your detector goes above that, it starts counting. It counts the number of the amount of time or number of clock cycles that you're over that threshold, and then you could use that to estimate the energy. And so we used a series of radioactive sources, starting from about 22 keV, although you can see the 14 keV americium peak somewhere in the shoulder on this detector, up to you could see the Compton edges of various photopeaks at the higher energies. Now, one thing that we noticed when we were looking at the dynamic range of these detectors was, even though we had a dual amplifier with a low range and a high range, the high range one only went up to about 200 keV, and our goal was 700 keV. So like I said, we were able to hit our low energy range, but we weren't able to hit our high energy range. This was just a bug, and we were able to fix it in V5. And so once we get that in the bench, we could test it, decide which amplifier is the best one, and then use that for future productions. But the really good news is that we were able to detect photo peaks from 22 to 122 keV in 90% of the pixels in both V4 and V3. And you could see the lovely spectrum on the right. The next one was the energy resolution. And so we were able to calculate basically the energy resolution in these various photo peaks. Our goal was to get 10% at 122 keV, and we're a little bit high on that one, but we're still measuring and trying to optimize this as well. You could see at the lower energies, we hit this. Actually, no, because the full width half max is in keV, and then the energy on the bottom is in keV. And so we have a lot of confidence that we're able to hit that requirement over the energy range that we have. Of course, when we have V5, we'll have to check it across the full energy range. So one of the real I think successes of the AstroPix project was how we've been able to reduce the per centimeter squared power from the original detector. And so the way that we care about power, because like I said, for gamma ray instruments, you want really large format detectors. And so we've been able to, starting with the original version, reduce the power by a factor of 100. One of the ways that we did this was we changed the pixel size. So in particle tracking detectors, you need relatively small pixels. In gamma ray detectors, you can have relatively large pixels, and it doesn't impact your performance. So that was part of the change. We were also able to reduce the timing requirement. For the original design, it had to have really tight timing requirements because there were bunch crossings that happened every 25 nanoseconds. We were able to relax that. We also were able to improve analog circuitry, streamline digital circuitry, and we've changed a lot of the clock and readout requirements. And so this has relatively steadily reduced the power. From V4 to V5, we knew that reducing the power wasn't as important because we've almost hit our mark. But then future iterations, we have a few other tricks that we can try to get to that final baseline. So one of the challenges that we have run into in these detectors is that we want to get full depletion. And so what that allows is just better energy resolution and full readout of the electron cloud that has been produced by the energy deposited in the bulk material. In order to achieve full depletion, in the plot on the upper right, you could see what you need is high resistivity or highly doped silicon wafers. And so you can look, this is a function of the bias voltage and the depletion depth that you can achieve for various different resistivities. So for relatively low resistivities, you need to really, really highly bias your detectors, and you still don't achieve that much depletion. As you go to higher and higher resistivities, lower biases enable higher depletion depths. And so for V3, our plan was to fabricate our devices on a relatively high resistivity wafer. The problem is that the foundry didn't properly handle the wafers, and so we ended up getting really high leakage current due to just a design defect in the way that it was processed. And so we weren't able to verify that we could get the full depletion depth with those detectors. At the lower resistivity wafers, the processing worked fine, but we knew that we weren't going to be able to achieve the depletion. And so we measured this in a couple of different ways. The first one was this edge TCT technique, where we scan a laser over the side of the chip when it's biased, and you could see the excitation of the chip, where the chip edge is at 0, and you could see where the depletion is occurring as a function of the scanned laser position. And we were able to verify this depletion depth using estimations from beam test measurements, where we were shooting protons at the detector and measured the time over threshold. And so for the iteration for V5, we have again some higher resistivity wafers, and so we're hoping to be able to verify the depletion with higher resistivity wafers in the next iteration, V5. And if this doesn't work, or if any issues arise, we can also do an additional processing step and bias the backside of these wafers to get the full performance results. Perfect. Okay, so this is just a brief summary kind of what I already talked about, going from the original design of AstroPix. The full design requirements were for a gamma ray telescope concept called Amigo X, and where we hit with V3, which was our first flight prototype, and V5, which is our second flight prototype. You could see this is a function of how we're going. The to be confirmed items are things that we believe we will hit once we have the chips in hand. The check marks are things that we have reached or are very close to what we've reached. And then the X's are ones we still need to confirm and are a bit more unsure. So overall, the project has been progressing very well over the course of the years. Okay, and so then I'm on my final slide, the wrap up. And so AstroPix has a lot of applications. We are planning to implement it in a sounding rocket payload. We are planning to implement it in a balloon payload, which you will hear more about today. It also has a lot of interesting space weather. There's interesting things potentially for heliophysics. So there's, I think, a lot of other ways that we can implement these detectors in various telescopes. And I've mentioned some of these. An additional use that I didn't mention is that these detectors are going to be implemented in the Barrel Imaging Calorimeter in the EPIC experiment, which is a ground-based nuclear physics experiment that's going to be located in Brookhaven National Lab. And they need 100 square meters of detector. So there's going to be a really large production run in the near future. And so we're barreling forward towards meeting all of our design requirements and implementing these detectors wherever it makes sense. And so I will leave it at that.